You guys.
Setting up for class right now.
Oh, yeah.
You set up for class right now?
Yeah. Or do you have a quick question I can answer real quick?
Well, I don't want to make you go through, obviously, my final, my work. This is the 2A, the homework.
Okay.
All I wanted to ask is, I left, in terms of my boundary conditions.
Yeah.
I left F1 y is 0 as well as theta.
Yeah, it's completely fixed.
Okay.
So it should all the first three rows should all be zeroed out.
Okay, and then this is pinned, so F2 of y is 0, but you have a mode, right?
Yes, correct.
And then over here you have both.
Yes.
Okay,
Yes.
and your overlap is at overlap of your global matrix is at your U2y theta 2 U3 sorry, U2y and theta 2 and U3y and theta 3.
There should be no overlap on 3 because there's only one element.
Oh, yes.
So
Okay,
the
so
only
this is my
overlap
overlap. Does it, I know,
Yeah, it should just be these two. It should be U2y and theta 2.
so you have
this
4
is-
terms that have.
Yes. Yeah, see, I think the best way for me to check these is just kind of take a screenshot of the work and then email it to me, and then I can gonna go. Although I've heard that there's some mistakes on this homework and stuff, but unfortunately I left my work for this back in my apartment, and so I need to go home and get it. And so
Yeah, I don't want to like
there's-
sift through this.
yeah, so there's like 3 people who kind of ask me stuff, and I've kind of labeled that for tomorrow.
Okay,
So yeah, just send it to me tonight, and then I'll go through all of them tomorrow.
Okay.
tomorrow.
and these terms here are cubed, right?
Yeah, LQ. Yep.
I saw your comment on the submission, and when I looked back to my submission, I didn't check and I didn't like submit like my original work because I first submitted it first, and then afterwards I went to go back and fix it, and I just excluded one of the pages.
Oh, I see. If you want to upload that work, if you submit it to me just like within the next hour or something, then I can go back and give you credit for it.
Oh, okay.
Yeah, just submit it soon, and then I'll do it tomorrow morning.
All right. Thank you.
Yep. Mhm. Hi, I'm going good. How about yourself? Good. Yeah, just gonna drink for my next class. Okay, it's 7 o'clock, so let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. It's week 6, and so it's right in the middle of midterm season, and so we have our midterm next week. And I'm sure probably you guys might have midterms either this week or the next week or the week after. So it's been a constant barrage of midterms until the end of the semester. So I know it's a stressful time, and so and I know these lectures are recorded, and so you can kind of view these whenever you want. Especially this lecture is kind of at a tough time, but I just want to say I appreciate you guys coming to the lectures either in person or virtually, because it's definitely a lot nicer to talk to people instead of just talking to just a webcam, which I've done before over the last couple of years. So I appreciate you guys coming. Okay, and so today the plan is to continue on with our lecture notes on frame equations. Okay, I think we stopped right in the middle of an example last time, and so we're going to pick up basically right where we left off. There really isn't that much to say about frames other than they're just kind of a bitch to solve because they are so big and so long. And so I'm not going to spend too much time talking about them, but I do want to spend a little bit of time talking about some a little bit of nuance in applying some of the boundary conditions. Because we've kind of been looking at boundary conditions in kind of a limited way. So I want to make sure we kind of talk about that, especially before we kind of head into the second part of the class. And then today, what I'm hoping for is maybe for the last 30 minutes, we'll be able to start our MATLAB implementation. Okay, so we're going to work on the MATLAB implementation today, and we're going to spend basically all class on Wednesday doing that as well. Okay, and what you'll see is that with the MATLAB, especially depending on how you feel about MATLAB, it is going to be a bit difficult to set up. But once you have it set up, then you can solve these frame equations, much more easily. Okay. So let's see, the homework's out there, and so that's good. And so are there any questions I can answer before we get started? Okay, let me just go ahead and close this door. Okay, all right, so let's go ahead and pick up where we left off. So actually, let me go back to the week 5 lecture notes, okay, and see where we are. Okay, and so last week we were looking at this example problem here, and so we were considering this kind of this 3-element 4-node structure. Okay, so we have basically a square where we have 3 elements. They're all frame elements. Okay. And we were interested in computing what the frame deformation was for this structure. Okay. And so we already went ahead and got started. And so we were defining the element stiffness matrices. Okay. And so we were starting with element A, and given all of its parameters here, we were filling in the element stiffness there. Okay. And then we went ahead and wrote it out for element B as well. Okay. Given that, our element stiffness for a frame was given by this this kind of big honking monster up here. Right. And so it's a lot to plug in. And so I know it's kind of a lot of tedious work. But what saves us in this problem is that a lot of the elements here are at 90-degree angles, right? And so because of that, either sine or cosine terms are just going to go away. And so we're going to be left with, a lot of zeros in these matrices, which is really nice. Okay. And so this was the element stiffness matrix for element A, given these quantities here. And this was the element stiffness matrix for element B, given that the orientation angle was 0 degrees for element B. Okay. And so next we're going to write out the element stiffness matrix for element C. Okay. And then we're going to start putting it all together. Okay, and so that was just a recap of last time. And so remember, for frames, it's nothing groundbreaking. It's nothing new. I mean, we're still following the same process that we've had before. The only difference is that it's a lot more calculations, because we really are, we're really, making it flexible for all different kinds of deformation, not just truss deformations, not just beam deformations, but all of them together at the same time. So that's kind of what makes it difficult. Okay. Okay. Any questions on this example before we start writing out the element stiffness matrix for element C? Okay. All right. So let me go back to week 6, just so my notes are organized. Okay. All right. So let's start writing out the element stiffness matrix for element C. All right. And so for element C here, first thing we're going to do is we're going to define the orientation angle. Okay. And so for element C here, the lower number node is up top, and the higher number node is on the bottom. And so the angle at which we have to rotate to get there is 270 degrees. Okay. And so of course, cosine of 270 is going to be 0. And sine of 270 is going to be -1. Next things we're going to compute is we're going to compute all of these kind of values here, because they show up quite often in the element stiffness matrix. And so we have 12i divided by L squared. This is 0.167 inch square. Okay. Next we have 6i divided by L. And so this is equal to 10.0 inch cube. And then finally, we have E over L, and this is 250,000 pound per inch cubed. Okay. All right, now we have the element stiffness matrix for element C. And so element C here is connected to nodes 3 and 4, and so we have an F3x, F3y, M3, F4x, F4y, M4. Okay. Oh, I always forget this. And so we have our 250,000 out in front. Okay. Right, then we have a column for U3x, U3y, theta 3, U4x, U4y, and theta 4. Okay. We have rows for U4x, U4y, theta 4, or excuse me, it starts with 3. Got a little bit ahead of myself there. Okay. So this is U3x, 3y, theta 3, U4x, U4y, theta 4. Okay, so let's go ahead and start filling these in. And so we start with the first row. And so the first row, we have a positive 0.167. Okay. Then we have a 0, Then we have a 10. We have minus 0.167, a 0 and 10. Okay. Since this is symmetric, I'm going to go ahead and write that into the first column. And so we have a 0, a 10, 0.167, 0 and 10. Okay. Next, we have the second row. And so the second row starts with a 10, 0, 0, minus 10, and 0. Okay. And then just like the first row, we're going to write that into the first column because it's symmetric. And so we have a 0, 0, minus 10, and 0. All right, we have a third row. So we have 800, minus 10, 0, and 400. Okay. Once again, we're going to write that into the third column. So that's a minus 10, 0, and 400. Okay. Okay. Then we have the fourth row in the matrix. And so the fourth row is 0.167, 0 and minus 10. Okay. And I'm going to write that into the fourth column as well, just to make sure that we're still all symmetric. Okay. Right. Then we have the fifth row.
Negative on fourth row first column.
Oh, wait, say again.
It should be negative on fourth row first column.
Fourth row, first column. Oh, that's negative. Yes, thank you. Yeah,
Okay.
I missed that negative. Thank you so much. Okay. All right, and so that's fifth row, fifth column. So that's a 10 and a 0. And then the bottom right is 800. Okay. All right, so now we have the element stiffness matrices for nodes or for elements A, B, and C. And so now we're ready to assemble. And so this is when things will get fun, I guess. So before we start assembling, are there any questions on this? Okay. All right. So next we're going to assemble. And this will probably take me, I'll probably have to move this around a bit, but let me go ahead and write the first column here. Okay. And so we're going to start with U1X, or excuse me, F1X, F1Y, M1, F2X, F2Y, M2, F3X, F3Y, M3, F4X, F4Y, M4. Okay. We're lucky in this problem because all the element stiffness matrices here have the same factor out in front, and so I'm going to go ahead and write that in. Okay. And so they all had a 250,000 out in front because that's the E over L factor. Okay. So we can go ahead and just kind of bank on that. Now I'm going to write in the columns. Since we have U1X, U1Y, theta 1, U2X, U2Y, theta 2. U3X, U3Y, theta 3, U4X, U4Y, theta 4. Okay. And then we have the corresponding rows here as well. So we have U1X, U1Y, theta 1, U2X, U2Y, theta 2, U3x, U3y, theta 3, U4x, U4y, theta 4. All right. So a little squish there, but you know, we have everything. We have everything there. And the other nice thing about this problem is that it's all sequential. And so element 1 is simply connected to element A is simply connected to element B, and element B is connected to element C. And so that'll help us in assembling this guy. Okay. Okay, so let's start with element A, right? So element A is connected to nodes 1 and 2. Okay. And so nodes 1 and 2 is going to be this upper block right here. Okay. Next, we have element B. Okay, element B here is nodes 2 and 3. Okay, so nodes 2 and 3 is all of these right here. Okay. Okay. And element C here is nodes 3 and 4. Okay. So nodes 3 and 4 is going to start here, go all the way to the end, and go down to the bottom, just like that. Okay. All right. All right, so before we start filling things in, let's make our lives a little bit easier for us. So we, you know, since we've done these, quite a few times already. So, I think everyone's kind of a veteran at this. And so before we start filling in our element stiffness matrices, let's go ahead and apply our boundary conditions. Our boundary conditions are pretty easy in this case. And so particular, I'm going to apply our fixed boundary conditions so that, because we know what those rows in the matrix are going to look like beforehand. Okay. Okay. And so our fixed boundary conditions are being applied on nodes 1 and 4. And so let's go ahead and apply those beforehand so we don't have to worry about it. Okay. Okay, so that's node 1, and then we're going to replace the f1x, f1y, and m1 with all zeros because it's a fixed boundary condition. Okay. All right, and we're going to do the same thing for the last row, for the last 3 rows. So the last 3 rows are for node 4, right? So we have a 1. Let me move that over a little bit. So we have a 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So it's a little squish on the bottom there, but and of course everything that's not covered in zeros here, we or not covered by any of the boxes there, we can fill in zeros as well. Okay. So here we have 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. 0, 0, 0, 0, 0, 0, 0, 0. Okay. So I know not everything's lined up well, but you know, but the number of entries there is correct. Okay, so any questions on this so far? Okay, so let's go ahead and fill in the rest of the numbers here. Okay. So we'll start with element A. Okay, so element A here, we're going to fill in for these entries right here. Okay, and so we have a minus 0.167. We have a 0. We have a 10. The 0, minus 10, 0. And then we have 10, 0, 400. Okay. Then we have the entries that overlap with element B. Okay. And luckily, we actually don't have that many overlaps because you know they're at 90-degree angles. Okay. So we have a 0.167 here, 0, 10, 0, 10. Then we start to have some overlaps here. And so we have a 10.0835, we have a 5, we have a 5, and a 1200 here. Okay. Uh, 10.0835. Let me make it a bit bigger. Oops. Okay, now we have the entries for element B. Okay, so we have a minus 10 here. We have a 0 and a 0. Okay, 0 minus 0.0835. 5, 0 minus 5, 200. Okay. And here we have a minus 10, 0, 0, 0 minus 0.0835, minus 5, 0, 5, 200. Okay. Then we have the overlapping terms with element C. Okay, so I'm going to do the overlaps in purple. And so we have a 10.167, 0, 10, 0, 10.0835, to a 5, 10, minus 5, 1200. And then finally, we have the entries for element C. So for element C here, we have a minus 0.167. Okay. We have a 0 and a 10. 0, minus 10, 0. Minus 10, 0, 400. Any questions on this? I know it's tedious. You know, it's supposed to be tedious, and so this is all build up so that we can write our MATLAB and we can enjoy the MATLAB code even more. Okay. Yeah. So actually, some of you actually emailed me over the weekend, and you've kind of already developed your own MATLAB code to solve these And so that's great. And so, you know, I've looked at a few of your MATLAB codes and you know, they're beautiful. And so we're going to take some elements from those and kind of implement them in our codes as well. Okay. All right. So what you have, that matrix there, you can go ahead and implement that in MATLAB. Although even this is kind of a big pain to do in MATLAB because it's a 12 by 12 matrix. Okay. But I did it for you. And so if you go ahead and input that into MATLAB, you end up with the following solution. Okay. And so if you solve this system in MATLAB, you get u1x, u1y, theta 1. All these are equal to 0, right? Because that was our fixed support. Okay, then we have u2x, u2y, and theta 2. u2x is 0.211 inches. Okay. u2y is 0.00148 inches, and theta 2 is minus 0.00153 radians. Okay. Okay, then we have u3x, u3y, and theta 3. So u3x is 0.209 inches. Okay. u3y is a minus 0.00148 inches. Okay. Theta 3 is a minus 0.00149 radians. Okay. All right, then we have u4x, u4y, theta 4. All of these are 0. Okay. All right. So any questions on this example? All right. So I have one more example here. Actually, this example here was showing an example with the distributed loading, but we kind of skipped that in this class, and so I'm just going to go ahead and skip to you know, what the problem itself looks like. Oh my goodness, this problem looks like a pain. Okay. All right. So let's do another example. Okay. And so here we have a two element system. Okay. It's only 2 elements, but it's but one element is angled, and so that's going to create kind of a pain in the butt for us. Okay. And so we have node 1, node 2, and node 3. Okay. This here's element A. This here's element B. Okay. And so we only have one node here that's actually going to move, and that's node 2. Okay. And so if we, let me give you the loads. And so we have a load here. We have a load here of 20,000 pounds. We have a load here of 20,000 pounds. Okay. We have a clockwise moment here of 160,000 pound inches. Okay. And then a counterclockwise moment here on node 3 of 160,000 pound inches. Okay. So let's, we'll say this angle right here. This angle right here is 45 degrees, okay? This horizontal length right here from node 1 to node 2. And so that horizontal length is 30 feet. And so the length of element B there is 40 feet as well, okay? So let me give you the material properties. And so they're going to be shared by both elements. And so we have the Young's modulus. And so the Young's modulus is 30 times 10 to the 6 psi. Okay. A here is 100 inch square. And then I here is 1,000 inch to the 4th. Okay. All right. And so just like we did for the last example, we're going to take this problem and we're going to, assuming all elements here are frames. Okay. Okay. And so if we assume both elements are frames, let's use this to compute the nodal displacements. Okay. And since the only node that's active here that's not fixed to a wall or not fixed to the ground is node 2. And so the only thing we're going to find here is the displacements for node 2. Okay. Okay. Any questions on the problem set up here? Okay. All right. And so the reason I'm not going to go through most of the details of this problem just because they're all mostly the same, but I did want to highlight something that's unique about this problem. And that's going to be this node 3 right here. Okay. And so what's unique about this node 3 is that you can see that we have both a fixed support as well as loads being applied. Okay. Okay. So this is a unique case, and so we haven't had a case that's like this before. And so we've only had cases where, if we were going to apply a load, they would be similar to load number for node number 2. And so in other words, we're applying a node or a load at a node that was free to rotate or free to displace. Okay. And so here we're applying a load at a node that's going to be fixed. And so, we have this dilemma of, where we are going to apply both a Dirichlet and a Neumann condition to this node, or are we? And so we'll see mathematically about what makes the most sense, and then we'll corroborate that, with what we physically kind of understand with these kinds of systems as well. Okay. But before we get that, we have to first write out our element stiffness matrices. Okay. Okay. And so let's start with element A. And so element A here, we can see that our orientation angle, if we draw a line from node 1 to node 2, the orientation angle for this is going to be 45 degrees. Okay. And so that means our cosine is going to be root 2 over 2. Our sine is going to be root 2 over 2. Okay. And our length here, since we have a 45, 45, 90 degree triangle, that means our length here is going to be 30 feet multiplied by root 2. Okay. because the length is the hypotenuse of this triangle. Okay. Yep. Because we're only given this horizontal distance right here. And so what we want is actually the length of the element itself. And so that's the hypotenuse of that triangle. And so if we use the kind of this 45, 45, 90, okay. Right? And so if this length is 30, actually no, it's not 30 root 2. I'm sorry. Kind of skipped ahead a little bit. And so it should be 30 divided by cosine 45. Yep. And so it'd actually be 60 divided by root 2. Yep. So this is 45 degrees. And so if cosine of 45 is equal to adjacent over the hypotenuse, then L is going to be 30 divided by cosine 45. Okay. So let's go ahead and compute the properties for this element. Okay. Okay, so we have 12i over L squared. Okay, because that shows up in the frame element stiffness matrix. And so that is 0.185 inch square. Okay. Next, we have 6i over L, and so that's 23.57 inch cube. Okay. And finally, we have E over L, and E over L here is 1.179 times 10 to the 5th pound per inch cubed. Okay. All right, and so unfortunately, this problem here has a lot of unfriendly numbers, and none of the entries are going to be 0. And so this is a problem that would probably take quite a while to compute everything. Okay. And so I'm going to go ahead and write this out because all the other elements that we looked at in the previous example were 90-degree angles. So since this one's a little bit unique, I'm going to go ahead and write this one out. But then I'm just going to go ahead and skip to the assembly after that. Okay. Okay. So this element stiffness matrix, we have F1y or F1x, F1y, M1, F2x, F2y, M2. Okay. Then we have U1x, U1y, theta 1, U2x, U2y, theta 2. U1x, U1y, theta 1, U2x, U2y, theta 2. Okay. Any questions on any of this before we start filling this bad boy in? Okay. All right. So let's go ahead and start filling this guy in. So from the top, and so let's do the first row first. And so we have a 4.42 times 10 to the 6. Okay. We have 7.07 times 10 to the 6. We have a minus 4.28 times 10 to the 6. We have a minus 4.42 times 10 to the 6. Minus 7.07 times 10 to the 6. And a minus 4.53 times 10 to the 6. Okay. Right, I'm going to take that first row and I'm going to write it into the first column. All right, so that's the first row and the first column. Okay, now we have the second row. Okay. So second row starts with 1.15 times 10 to the 7th. Okay, so there's no 7 there. Then we have a 2.64 times 10 to the 6th minus 7.07 times 10 to the 6th minus 1.15 times 10 to the 7th. And then a 2.64 times 10 to the 6th. Okay. Okay. All right, so that's the second row, second column. Next, we have the third row. Okay. And so that's the third row in the third column. Okay. And of course, all of this is detailed in the lecture notes. And so, I know it's kind of a pain to write these down, so you can just go ahead and check there. Okay. But just for the sake of completeness, I will go ahead and finish writing this out. Okay. It's a little bit clearer. All right, so that's our element stiffness matrix for A. So I wanted to show this to you guys because this is kind of a worst case scenario. And so when the angle is not nice, when all the numbers are not nice, then you end up with a pretty nasty thing. And so I think naturally, when we do these problems, what we hope for and what we're looking for are kind of nice numbers that are not kind of irrational decimals. But sometimes it do be like that sometimes. And so sometimes you end up with some really nasty numbers, and that's just kind of how the cookie crumbles. And so if you get something like this, don't kill yourself trying to check all your work. More likely than not, that just actually is how it is. Okay. All right. So any questions on this? Okay. Okay, and so that's element A. And so I'm not going to repeat this for element B. So element B, Element B is not as bad because the orientation angle for this is 0, but it's kind of a lot of writing. So element B computed as well. Okay. But what I did want to get to was the assembly, because remember the thing that's unique about this problem was that we had a kind of a Dirichlet boundary condition as well as a Neumann boundary condition apply at the same time. And so I want to make sure that we go over what you do in these kinds of situations. Okay. Okay, so now we're going to go over assembly and boundary conditions. Okay. And so here we only have 3 nodes, and so thankfully our global system is only going to be a 9 by 9. Okay. All right, so there's our system. Okay. Let's get the assembly out of the way. And so let me go ahead and fill in the entries for element A and element B. Okay. And so element A, of course, is going to be nodes 1 and 2. And so that's going to be these entries right here. Okay. Right, and so that's going to cover that box there. So all of the entries with nodes 1 and 2 associated with them. Okay, then we have element B. So element B is nodes 2 and 3. And so that's going to be all of these entries. Okay. Just like that. Okay. All right. And so, of course, with the assembly, you would go ahead and fill in those boxes with the appropriate entries from the element stiffness matrix. And for anything that's overlapping, you would just add the entries just like we've done before. Okay. But now I want to talk about the boundary conditions. So let's do what we usually do for the Dirichlet boundary conditions. Okay. And so for the fixed nodes, we have nodes 1 and 3. And so that means in terms of the matrix, we're going to have a 1, 0, 0, 0, 0, 0, 0, 0, 0, okay, 0, 1, 0, 0, 0, 0, 0, 0, 0, and then 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay. And then, of course, that means we're going to change the right-hand side entries to 0 as well. Okay. And then we're going to do the same thing for the last 3. Okay. Okay, so that's what we would normally do for a fixed support for nodes 1 and 3, right? And so we would change the entire rows. And so we change them to have a 1 on the diagonal and 0 on all the off diagonal terms. And then we put a corresponding value of 0 on the opposite side vector. Okay, and so in the forcing vector. But what was unique about this problem is that we also had loads that were being applied on nodes 2 and 3, right? And so in fact, we had F2y. F2y was equal to a minus 20,000 pounds. Okay. M2 was equal to a minus 160,000 pound inches. Okay. F3y was equal to a minus 20,000 pounds. Okay. And then M3 was equal to a positive 160,000 pound inches because it was a counterclockwise moment. Okay. All right, so let's go ahead and fill those in. And so let's start with node 2. And so node 2, we had no F2x, and so F2x is going to be 0. Okay. F2y, we can go ahead and fill that in, is minus 20,000. Okay. And then M2 was a minus 160,000. Okay. Okay, so all that's good. And so that's all that we've done before. Okay. So now what do we do about these guys? Okay, so actually, F3y, we have nothing there, so that's fine. Okay. And so the more important question is, what do we do with F3y and M3 in our global system? Okay. Normally what we would do is that, we would change these entries to be minus 20,000 and 160,000. Or positive 160,000, excuse me. Right. So that's what we normally do when we have a load type boundary condition, is that we would change the entries in the forcing vector to reflect what those loads are. Okay. But here's a unique case because we're actually applying those loads at a part that's supposed to be fixed. Okay. Let's kind of remind ourselves what these fixed support equations look like, right? And so if we were to take, let's take, for example, this row right here, okay, and then multiply by this vector, okay? And so we take this row and multiply it by the solution vector. All we would get is U3y, right? Okay. That's what you get when you do like the row times the vector multiplication, okay? And if we were to put this load here on the left, then we would get U3y is equal to minus 20,000, right? And so that tells us that our y displacement for node 3 is going to be 20,000 somethings, right? Like 20,000 inches. And so obviously, that's not what we want, right? So what we want for node 3 is for it to be fixed, okay? And so this is what we should not do. And so in order for us to respect or still respect the fixed support, if you have a case where you have a load and a support being applied at the same node, what you should do is that you should let the support or let the Dirichlet boundary condition take priority. Okay? And so what that means that you kind of just ignore that the loads are being there to begin with. Okay. And so you're going to ignore this. Okay. And so instead of putting a minus 20,000 and 160,000, you just have 0, 0 there, as if, as if that load didn't exist. Okay. And by doing that, then you're able to, still respect the fixed supports, which in most cases, that's going to be more important than the loads themselves. Okay. Right. And so this might seem kind of strange because because we have a situation where, it kind of feels like we're ignoring a big part of the problem. We're ignoring a big part of the loads that are being applied. But remember, the first thing that we're solving for here is the displacements, right? Because our displacements are our primary variables. And so, the thing we have to prioritize is we have to make sure our primary variables are computed to what they should be. And so what they should be is, respecting all of the constraints, all of the fixed supports that are added to it. Okay. And so, that's something important that you need to remember, that when you have situations like this, you kind of just ignore the loads being there to begin with. Okay. All right, any questions on this? Of course, because if you think about it, and if you take any object, right? So let's say I take this mouse, right? And if I put this mouse on this table, then the table kind of applies a fixed support on the mouse. And so the bottom of the mouse can't move, right? It doesn't matter how much force I apply onto the mouse, right? The bottom of the mouse should not move, right? And so whenever you apply a force onto a part that's a fixed support, normally you would expect the fixed support to win, right? And so if you apply, even a structural case, let's say you have two parts that are welded together. If you apply a force on a part that's welded to a wall, then you would expect that part not to move unless the weld kind of breaks off, right? And so this is kind of reflecting that. Okay. In reality, of course, if you apply a load close to a support like this, I think what you would generally expect is a high amount of stress kind of in the vicinity of the support. Okay. And so in order to capture that, what you would need to do is you would kind of need to refine this frame element so that you have kind of an appropriate amount of node density, element density. And so even though the node that's directly attached to the wall is fixed, then the nodes that are close to it can react to whatever mode is there. Okay. But because we're kind of taking this entire element as kind of one beam right there, then we have to respect the supports first. And so the supports have to be, their effects have to be, maintained. And so, mathematically, the only way to do that is just to kind of ignore any loads that are placed on the supports as well. Okay. Okay. So any questions on that? Okay, so I did want to talk about one more thing, which is kind of a twist on the Dirichlet boundary conditions before we start talking about MATLAB. Okay, and that's what you have to do, or mathematically what you have to do when you have a non-zero Dirichlet boundary condition. Okay. Okay. All right. So far, when we talk about Dirichlet boundary conditions, we've mostly just talked about fixed supports. Okay. Okay. You've called them fixed supports. We've done pin supports, we've done roller supports as well, but they all kind of have the same effect, which they set the displacement or they set the rotation equal to 0. Okay. right? And so fixed support means that it's not going to displace, it's not going to deform, right? And so we did that by applying a 0. Okay. Mathematically, the way that we applied this was that we put a 0 in the forcing vector. Okay. Along with the usual, changing the row to have a 1 on the diagonal and 0s everywhere else. Okay. Okay. And so visually it looks something like this. So we have our right-hand side, our forcing vector. We have our left-hand side matrix, our global stiffness matrix, and we have our solution vector. Okay. And so let's say that we set the first node, degree of freedom equal to 0, right? And so this is what we did, right? So let's say this is like U1x or something like that. I want to talk about this part of what we did. Okay. And so that part basically sets the displacement equal to 0, right? But what we'll see, especially in the second half of the class, once we get into kind of more generic or general finite elements, is that we're going to come across situations where we set Dirichlet boundary conditions to non-zero values. Okay? Okay. And the context that we're going to be seeing this a lot is in heat transfer. Okay. And so the equation that we're going to work on mostly for the second half of the class is going to be the heat equation. Okay. And the heat equation has Dirichlet and Neumann boundary conditions just the same. It's just that they have different physical interpretations. Okay. And so for the heat equation, a Dirichlet boundary condition takes the form of a specified temperature. Okay. Okay. All right. And so, as an example, we're going to be working on square domains a lot. Okay. And so let's say that on one side of this plate here, we have a specified temperature of 50 degrees Celsius. And on the other side of the plate, we have a specified temperature of 25. Okay. And then for the top and bottom, they have something as well. Okay. And so these specified temperatures here, these are our Dirichlet boundary conditions. Okay. Okay. And so to apply these into our matrix, we have to make sure that the entry that we put in the forcing vector is our specified Dirichlet value. Okay. Okay. Because remember what this row represents, right? So this row represents, if we take this row and we multiply by this, okay, what we're saying is that U1x, okay, that's after we apply this multiplication, that's equal to 0. Okay. If we do the same thing for this thermal case, okay, Okay, so let's say that T1 is right here. Okay. Right. So node 1 or T1 there is sitting on the boundary, right? And so we have to set T1 is equal to 50 degrees C. That's our boundary condition. Our boundary condition says that any node that's sitting on that left boundary has to have a temperature of 50 degrees. Okay? And so mathematically, the way that we apply this is that we, let's say that we have our first row in the matrix like that. Okay. And so if we perform the vector multiplication of these two vectors here, we end up with T1. Okay. And so to make sure that our T1 here is equal to 50, what we need to put in the forcing vector is exactly that 50 right there. Okay. And so we put 50 right there. This tells us that 50 is equal to T1. Okay. And that's exactly equal to the boundary condition that we need to specify. Okay. And so it's a little twist on how we specify this Dirichlet values. And so up to this point we've just been putting a 0 on that forcing vector. But the only reason we've been doing that so far is that, in structural mechanics, most of the time when you apply a Dirichlet boundary condition, it's in some kind of support. And so you're basically constraining the displacements to be essentially 0. Okay. And so, we put a 0 there. We put a 0 there to reflect that, we're constraining this displacement or deformation to be 0. But for other cases that we'll see, different kinds of Dirichlet boundary conditions. You need to make sure that on the forcing vector you apply the correct temperatures there. Okay. Yeah. Question.
Is that you can zero out the force matrix and you actually apply the temperature that's
Exactly. Yeah. Yeah. So for the matrix, we're doing the same thing, and so we're putting a 1 on the diagonal, and we're putting zeros everywhere else. The only difference is in the forcing vector on the left. Mm-hmm. All right, so I wanted to make sure, just because we're talking about boundary conditions up here, so I thought this would fit here. So this is going to take effect a lot, once we're in the second half of the class. Okay. All right, any final questions on this before we move on to the MATLAB implementation? Okay. All right, and so we don't have that much time left, but I did want to start the MATLAB, okay, just to get you introduced to it. Okay. So I don't want this. Okay. And so if you go to our course website here, okay, EGME 541, and you go to week 6. You'll see that there are two resources that I have for you. And so first, I have here a PowerPoint presentation, which is what's going to guide us. And I also have a starter code here. Okay, so if you click on the starter code, let's go ahead and download it. We're not going to have time to work on it today, and so you don't have to worry about scrambling to start MATLAB or anything. But I just wanted to show you it. Okay. And so this code here is kind of the starter, and so we're going to be working on this code all of Wednesday, and maybe Monday if things spill over. Okay, and we're going to be filling in everything in this code to solve frame problems. Okay, so it's a little bit of a beefy code. Depends on how much experience you have with MATLAB. And so it's about 240 lines, but I've written most of the structure for you. The only things I want you to fill in are just kind of the theoretical parts. Okay, and so that's what we're going to be doing on Wednesday. Okay, and then to kind of guide us in that exploration, I have these slides. And so let me go ahead and download these slides first. Okay, and then we'll just kind of start talking about them. For now until the end of class. Okay, so can everyone in Zoom, can everyone see the slides?
Yes.
Okay, good. Okay, and so ignore the date. And so this is obviously spring 2022, but I haven't changed these lecture notes since then. Okay, and so these lecture notes, even though we'll be focusing on frames, because I think this method suits frames really well, because it's going to simplify a lot of the calculations for you. But just to look ahead a little bit, this method here can be applied to any kind of direct stiffness problem. And so, we'll do the frames together. And so we'll do the frame equations together in class on Wednesday. But your next homework assignment after the midterm is going to be to implement these methods for a 2D truss. Okay. And so I figured that would be a kind of a good homework problem for you guys to work on your own, because a truss is not as complex as a frame, but it still kind of illustrates a lot of the core kind of programming concepts that we're going to go over in this method. Okay. Okay, so introduction. And so introduction, so far we've learned how to use the direct stiffness method, to perform basically FEA on structural systems. And so that includes spring elements, truss elements, beam elements, and finally frames. Okay. And so far, most of the calculations that we've been performing have been done by hand. And that refers to like the element stiffness matrices, right? And so all those have been by hand so far. But we can write a code to do all this work for us. Okay. And this goes beyond, I think, what most people have been doing so far, which is, once you have the fully assembled global stiffness system, then you use MATLAB to compute the solution. And so this is going to go beyond that. And so this is actually going to construct all the element stiffness matrices for us. It's going to do the assembly for us, and it's going to do the solution for us as well. And so this kind of goes beyond kind of what we have and what we've done in class. And the idea is to kind of make a general code so that, in the end, all you have to input is just the details of the geometry, the details of the material properties like the Young's modulus and the moments of inertia, as well as the boundary conditions. And then MATLAB is going to do all the work for you. Okay. And so hopefully, once this code is implemented, it'll be a lot easier to solve a lot of these systems, because you just have to kind of just punch in a lot of these things, initially, and then MATLAB is going to do all the kind of heavy computations for you. Okay. Okay, and so even though it's code, I know people have varying degrees of comfort with code. I think what's going to help us kind of make sense of the code is that we're going to follow the exact same method that we've applied so far. Okay. And so the finite element method that we've been following so far is to, first of all, compute the element stiffness matrices for all the elements in a stationary coordinate system, right? So that's always our first step. The next step is to assemble all the element stiffness matrices into a single global linear system. Okay. Third is going to apply all the boundary conditions, and fourth is to solve. Okay. And so our code is going to follow this exact same logic as well. And so what you'll see in the code is that there are different sections of the code that follow these, these steps kind of exactly. Okay. And so it's going to take a bit of work to implement this code for the first time. But the idea is that once it's implemented, you can use it to solve, very complicated stiffness problems. Okay. And I structured this code in a very kind of, deliberate way, in that, if you opened up ANTIS or you opened up any kind of finite element code, of course, it's going to be different than the code that we're going to write here. But the general structure and the general data structures and the general logic that we follow is going to be the same as those codes as well. Okay. Well, full disclaimer, I haven't looked at the ANSYS code. I haven't worked for ANSYS before, but I have worked in development on a lot of very complex finite element codes, and they all use the same structure. And so, I wanted to make kind of a miniature version of that for you guys so that you kind of see the logic on how these codes are constructed. Okay. Any questions on this so far? Okay. All right. So next, I want to talk about data containers, and so these are going to be the variables that we're going to be using. Okay. And so if you remember from our MATLAB tutorial, we spent a lot of time talking about variables, right? So variables can store numbers, they can store vectors, they can store matrices as well. Okay. And so how we store all the data, so how we store all the element stiffness matrices, this is probably going to be the most important thing of our code. Okay. Because if you can understand how the data is being stored, then a lot of the logic of the algorithms, combined, of course, with the knowledge that we've already gained in this class, those start to make a lot more sense. Okay. And so in particular, normally what we would do for these problems is that when we take things like the geometric properties, things like the material properties, we would kind of write those down by hand and kind of, compute those on the fly. Okay. The difference here is that, for the code, we have to store all of this data into variables so that the code can access them later on. Okay. And throughout this presentation, I tried my best to kind of try to visualize a lot of these containers as much as possible. Because I think when you're looking at MATLAB code and you're saying like, yeah, this is a variable and this is what goes inside it, I think what really helps is to have kind of that visual representation of what that data container actually looks like, so that you can kind of see in real time, as we're inserting stuff and as we're kind of referring to stuff. So I did my best in these lecture notes to kind of start to kind of visualize that for you. And so try to keep that kind of visual representation of the data containers in mind as much as possible. Okay. And so, of course, we talked about it. So the starter code is available for you on Canvas. And so if you want to get a head start on it, you can go ahead and look, and you can kind of read ahead in the slides. But the plan is to fill in that code together on Wednesday. Okay. And all the key parts that I want you to fill in have a to do. Okay. And so anything that doesn't have a to do, you don't have to change it in the code. But the only things we're going to be filling in is the to do parts. And so we're going to fill those in together on Wednesday as we kind of explain kind of the logic behind those things. Okay. Okay. So any questions on this before we wrap it up for today? Okay. All right. And so that's all we got time for today. And so on Wednesday, we'll start with the MATLAB stuff. And so we'll open up MATLAB. We'll start with this code, and then we'll start filling it in. Okay. And so it'll be our kind of our first really big MATLAB project in this class. Right? All right, so thank you guys for coming out today. I know it's a really busy time, so and I know today wasn't the most exciting lecture. All we did was write matrices for an hour and a half, and so I know it's kind of boring, but I appreciate you guys sticking in there with me. So have a great evening, everyone. Wednesday will be more exciting, I promise. We'll be working in MATLAB, and I'll see you then. Yeah. Okay. Yeah. So it's true that each of these numbers, they can only displace longer. But these numbers are these are the global poles for the station. So X this way, Y this way. So for this spring, I think it makes the most sense for the spring. It's going to roughly like this. And so if you break down the displacement, it's going to go. But we could break up the vector like this. Yeah, those are kind of solve them all within the same coordinate system. Everything related to well. I mean, like you want to yeah. Yeah, and so we just break it up into the X and Y. Yep. Yeah. Yeah, because if you look at kind of a actually let me just bring my iPad here. So the typical beam element looks like So what we say is that we have F1. F2y. And so because this M line is going clockwise, then we say that the actual M1 minus. Yeah, so the minus sign kind of flips the sign just because this is the kind of or clockwise. So that's why you get the opposite. So you just have to flip it because of. Yeah. Yeah.
You know when you're gonna have a study guide?
Tomorrow.
Tomorrow?
Yeah. Yeah, and then I'll have the poll until Friday at noon.
The poll on, whatever, commenting on.
Exactly. Yeah. So because I Friday afternoon are those free. So that's what I'm reporting. So I have three of my classes. They turn next week, so I have to report 3 days. So.
Okay.
Tim, any final questions before I close up the Zoom room? Okay, all right. So I'm gonna go ahead and close the room. So have a good night.
I used to go every year.